Uno, dos, 1, 2, 3, 4.
We are now ready to prove the main theorem in this section. That is theorem 7 in section 9.3, that R is a UFD if and only if R bracket X is UFD. And we already saw at the beginning of the lecture that R bracket X is UFD implies that R is a UFD. So now we'll suppose that R is a UFD, and let's say that the field of fractions of R is F. And we want to show that R bracket X is a UFD. So we're going to take a polynomial P of X in R bracket X. And we're going to show that first, we can write P of X as a finite product of irreducible elements in R bracket X. And then we'll show that this factorization is unique up to associates. So the first thing we're going to do is we're going to suppose that the content of P of X is D, that the GCD of the coefficients of P of X is D. And as we saw in the last video, that means we can write P of X as D times P prime of X, where P prime of X still has coefficients in R bracket X. And the GCD of the coefficients of P prime of X, the content of P prime of X, is 1. And we know that R is a UFD. So R can be factored uniquely into a product of irreducible elements in R. Sorry, D can be factored uniquely into a product of irreducible elements in R. What's true about those irreducible elements in R? Well, they're all in R bracket X as polynomials of degree 0. And if you're irreducible in the ring R, the corresponding degree 0 polynomial of R bracket X is still irreducible in R bracket X. So D can be factored uniquely into a product of irreducibles in R. And each of these is still irreducible in the larger ring R bracket X. So what does that mean? We're going to factor P of X by factoring D and factoring P prime of X. And the factorization going on over here for little d is unique because R is a UFD. So it's enough to show that P prime of X can be factored uniquely into a product of irreducible elements in R bracket X. So that means for the rest of the proof, we're not going to write P prime anymore. We're just going to assume that the degree of P of X is greater than or equal to 1, that this really is an element in R bracket X that's not secretly some element of the ring R living in R bracket X as a polynomial of degree 0. So the degree is greater than or equal to 1, and that the GCD of the coefficients of P of X is 1, that the content of this polynomial is 1. OK. Now, we have this polynomial P of X that's in R bracket X, but we can think of it as an element of F bracket X. And since F bracket X is a UFD, we can factor P of X uniquely into a product of irreducible elements in F bracket X. And now we'll apply Gauss's lemma, which says that this factorization in F bracket X gives us a factorization into a product of elements in R bracket X that are F multiples of the irreducibles in the F bracket X factorization. So what does that mean? It means, remember we had like a factorization of P of X equals capital A times capital B in F bracket X. And there was a little a and a little b where little a of x was equal to R times capital A of x, where R is some element in the field F. So each one of the elements in this factorization in R bracket X is some field element times the corresponding irreducible in the F bracket X factorization. OK, and this is the sentence that I find most confusing in Dummett and Foote. What they say is because the GCD of the coefficients of P of X is 1, in this product of P of X as a bunch of things in R bracket X, the GCD of the coefficients of each one of those polynomials is 1. That's true, but I don't think it's obvious that that's true. So why is that true? Exactly because content is multiplicative. The content of P of X is 1. So if we have P of X equals a product of a bunch of polynomials in R bracket X, the content of each one of those polynomials is also 1. Remember, content is only well defined up to a unit, so it's a unit, whatever. The content is 1. So each one of these factors in this R bracket X product has GCD 1. And what that means is we can apply this corollary 6 to Gauss's lemma to each one of those factors that occurs in this product of P of X or this factorization of P of X as a product of a bunch of things in R bracket X. So each one of these R bracket X factors here is irreducible because the GCD of the coefficients is 1. So they're irreducible in R bracket X if and only if they are irreducible in F bracket X. Where did these factors come from? They were a bunch of irreducibles in F bracket X. To get the ones in R bracket X, you multiply by some field elements, but they're still going to be irreducible in R bracket X. Because if you take an irreducible in F bracket X and you multiply it by a unit, it's still irreducible. Okay, so what does that tell us? That says that P of X can be written as a finite product of irreducible elements in R bracket X. And what did we use to get here? We used the fact that R is a UFD to reduce to the case that P of X has positive degree and the GCD of the coefficients is 1. We used Gauss's lemma to go from a factorization in F bracket X to a factorization in R bracket X. And then we used that content is multiplicative to see that the GCD of the coefficients of each one of those elements in R bracket X, they all have GCD 1, so they're all irreducible by this corollary of Gauss's lemma. Okay, so we see that we've satisfied half of what it means to be a UFD. P of X can be written as a finite product of irreducible elements in R bracket X. So now we just have to show that this product of irreducible elements is unique up to associates. Where is that uniqueness going to come from? The uniqueness in this R bracket X factorization will come from the uniqueness in the F bracket X factorization that we get from this ring being a UFD. So I'll pause and erase and explain how that uniqueness part of the argument goes. Let's finish the proof of this main theorem that R is a UFD implies that R bracket X is a UFD. We started with this polynomial P of X, and we have now seen that we can write it as a finite product of irreducible elements in R bracket X. We have to show that this factorization is unique up to associates. And the main idea is that the uniqueness of this factorization in R bracket X is going to follow from the uniqueness of the factorization of P of X in F bracket X. So let's suppose that we have two factorizations of P of X into products of irreducible elements in R bracket X. Q1 of X times Q2 of X times QR, and then Q1 prime times QS prime. All right, so we know that the GCD of the coefficients of P of X, the content of P of X is 1. And because content is multiplicative, the same is true for each polynomial in both of these products. So the GCD of each Qi and each Qj prime, the GCD of the coefficients is 1, the content is 1. So one thing that means is that in R bracket X, there are irreducible elements that have degree 0, right? The irreducibles of R. But that would mean that you have a polynomial of degree 0 that is irreducible. That means that there is some irreducible factor dividing all of the coefficients. In particular, if you have an irreducible in R of degree 0, the content is not 1. So since the content of each Qi and each Qj prime is 1, the GCD of the coefficients is 1, that means that each one of these irreducibles in R bracket X has positive degree. And now by corollary 6, if you have a polynomial in R bracket X and the GCD of the coefficients is 1, it's irreducible in R bracket X if and only if it's irreducible in F bracket X. So that means that each one of these is irreducible in F bracket X. And now we're in good shape because now we have two different factorizations of P of X into products of irreducibles in F bracket X. And F bracket X is a unique factorization domain. So by the unique factorization in F bracket X, that means the number of these irreducible factors is the same, that R equals S. And we can rearrange these factors so that each Qi of X is associate to Qi prime of X in F bracket X. So what that means is each one of these Qi of X is equal to some unit in F bracket X times Qi prime of X. So what do we want to show? We want to show that these factorizations are unique up to associates in R bracket X, so that we can rearrange so that each Qi prime is equal to Qi of X times a unit where that unit is in R, or is in R bracket X, but the units in R bracket X are the units in R. And right now we know that we can write each of them as a unit in F bracket X times, each one of these differs by a unit. And the problem is that R doesn't have as many units as F, so there's still something to prove. Okay, so let's suppose that we have two polynomials, Q of X, Q prime of X in R bracket X, and Q of X is equal to A over B times Q prime of X, so what else do we know about these polynomials? Not only are they polynomials in R bracket X, but in the situation we're in, we know the GCD of the coefficients is 1 for each one of these. So we have two polynomials, Q of X, Q bracket X, Q of X, Q prime of X in R bracket X, and each has content equal to 1, and A and B are non-zero elements in R, such that Q of X equals A over B times Q prime. Clearing denominators, an idea that we've seen before, B times Q of X equals A times Q prime of X. And now we have this equality of these polynomials. So the GCD of the coefficients of these two polynomials has to be the same. And the content over on the left-hand side is B. And the content over on the right-hand side is A. And OK, so this doesn't mean that A is equal to B, right? R is a UFD. Content is only well-defined up to a unit, right? So this doesn't mean A is equal to B, but it does mean that A is equal to some units in R times B. So remember, A greatest common divisor is only defined up to a unit in the ring. So A equals U times B for some U in R. But then what is A over B? This is a unit in R. So that means that this is now exactly the situation we're in here. We see that Qi of X is associate to Qi prime of X in R bracket X. Not just in F bracket X, but in R bracket X. And that is the last thing we needed in order to see that this factorization is unique up to associates in R bracket X. And R bracket X is a unique factorization domain. OK, so I'm going to pause and erase, and I'll talk just a little bit, very briefly, about some additional issues related to factorizations in R bracket X. Let's next mention a direct corollary of this theorem, that R is a UFD if and only if R bracket X is a UFD. If R is a UFD, then a polynomial ring, not just in one variable with coefficients in R, but in an arbitrary number of variables with coefficients in R, is a UFD. So what's the idea? Well, OK, Z is a UFD, so Z bracket X is a UFD. Z bracket XY is defined inductively as Z bracket X bracket Y. But Z bracket X is UFD. So Z bracket X bracket Y is also a UFD. And so on. 3 variables, 4 variables, 5 variables. So for finitely many variables, that's the proof. You do induction on the number of variables, starting with the base case of polynomial rings in one variable. For the general case, where you have this arbitrary infinite number of variables, you can use the definition of the polynomial ring in an arbitrary number of variables as the union of all of the polynomial rings in finitely many variables, r bracket x1, r bracket x1, x2, and so on. All right, so the last thing that I want to talk about in this lecture is what happens if R is not necessarily a UFD, but is just an integral domain. So what can you say about factorizations in r bracket x? So let's take a polynomial p of x in r bracket x, where r is an integral domain, not necessarily a UFD. And let's suppose that p of x is a monic polynomial that is reducible. So this is the case we're considering, monic reducible polynomials in r bracket x. So what does that mean? P of x equals a of x times b of x, where these are two polynomials in r bracket x, and they're not units. OK, the leading coefficient of p of x is 1. And what is the leading coefficient? It has to be the product of the leading coefficients of a of x and b of x, because we're in an integral domain. OK, so what does that mean? Both of these coefficients, the lead coefficient of a of x and the lead coefficient of b of x, they're both units. So that means that we can write a of x as some unit u times a prime of x, and we can write b as some unit v times b prime of x, where u and v are units, and a prime and b prime are now monic polynomials. We take this unit that is the lead coefficient, and we factor it out in both cases. So what does that mean? Now p of x is equal to u times v times a prime times b prime. And the leading coefficient on the left-hand side for p of x is 1. And the leading coefficient on the right-hand side is u times v. So that means u times v equals 1. So what are we seeing? We're seeing that p of x is a product of a prime of x times b prime of x of two monic polynomials in r bracket x. And they're not units, right? Like if a prime was a unit, then a would have been a unit also. And we suppose that these are not units. So a monic polynomial that has degree 0 is 1, so is a unit. So that means these monic polynomials are not units, which means that in particular they have degree at least 1. So we have a product of p of x is equal to a prime times b prime. These each have degree at least 1, which means they each have degree also less than the degree of p. The degrees on the right-hand side add to the degree on the left-hand side. So I'm going to pause and erase, and then I'll write up these observations as a quick proposition that will be quite useful in our next lecture. We can summarize this discussion by saying that when R is an integral domain, a non-constant monic polynomial, p of x in r bracket x, is irreducible if and only if it cannot be written as a product of two monic polynomials of smaller degree. So what have we seen just before this is that if your monic polynomial is reducible, that it can be written as a product of monic polynomials of smaller degree. So I'll let you think about the other direction. OK, if R is an integral domain that is not a UFD, it is not generally true that p of x monic and irreducible in r bracket x implies that p of x is irreducible in f bracket x. Remember, Corollary 6 says that this statement is true when R is a UFD, that if you have a monic polynomial in r bracket x, it's irreducible in r bracket x if and only if it's irreducible in f bracket x, where f is the field of fractions of R. So I want to finish this lecture by just giving an example here. Let's say that R is z adjoint 2i. So it's everything that can be written as a plus b times 2i, where a and b are integers. The field of fractions of R is q adjoint I. So it's f equals q adjoint I. That's not so difficult to see. Let's consider the monic polynomial p of x equals x squared plus 1. This is irreducible in r bracket x. Why? Because it cannot be written as a product of two monic polynomials of smaller degree. So there's no alpha and beta in this ring R, so that x squared plus 1 equals alpha plus x times x plus alpha times x plus beta. You can just expand it out and see that this can't work. But in the field of fractions, p of x is x plus I times x minus I. So it's certainly reducible in Q adjoin I. So irreducible in R bracket x, reducible in F bracket x. And what does that mean? Corollary 6 says that this can't possibly happen if R is a UFD. So corollary 6 is giving us a way to see that certain rings are not UFDs. In particular, Z adjoin 2I is not a UFD. And what's kind of neat about this is you think of a UFD as being a ring in which factorizations of elements into products of irreducible elements are unique. And here we're showing that Z adjoin 2I is not a UFD in a way that doesn't involve writing down an element and then factoring it into irreducibles in two different ways.